Hi, it's time for another math easy solution. Today I'm going to go over another applied project, and this time look at the one titled Radiation from the Stars. And yeah, this is just a very interesting applied project, which is at the end of the section on infinite sequences and series, which I've been doing previously quite extensively. Anyways, let's just jump right in. Also, just a note: I've added a link tree as well, so you can go over here, linktree slash math easy, and has basically a bunch of links there for all my stuff, so you can go and check it out. And also, just a note, as always, if you don't have time to watch this whole video, you can, in this case, you could play this video at a faster speed. Top secret life hack: your brain gets used to faster speed. And here's a tutorial over there that I made, and also you could download and read the notes. And you could read notes. You could download, read the notes. Link in the description below, or also read the notes in article format on the Hive blockchain. And you can watch a video in parts. Timestamps of all the parts are in the description. You could even skip this mini intro that I always do. And also here's the browser extensions. Here's the video speed. And also you can increase video audio. It's pretty interesting. And these ones also I recommend text-to-speech on the browser. And also for Android app right here. You can just turn any paragraph or PDF document into text, which into speech, so you can listen to it. If that works for you, and it's pretty amazing. Anyways, let's just keep going further. Yeah, I just want to make a quick note. So MES note: sharpen your mind with mathematics. So in my last video, I gave an update about my progress for MES Science 3, which will now be on microbiology and genetics. So I've spent 5+ months researching all things COVID-19 and biology in general, but at the expense of making my usual math videos. Thus, I'm taking a quick break to get in a math video. So that's this applied project. So I've always viewed mathematics as one of, if not the best, tools to sharpen the mind, and it was the driving force in deciding to create math easy solutions in the first place. Going further, so mathematics has several key aspects that make it applicable to all areas of life. So first of all, the assumptions and principles are clearly defined, and there's a logical progression of steps when making derivations. And then it also results in exact or quantifiable answers. And different answers can be modeled by changing assumptions / principles. And yeah, this is just a note here. This is the usual technique of corporate / government deception. Because yes, don't just accept any statistic or output of a model, because it's all dependent on underlying assumptions and so on. So, and you can also individually validate the derivation of others by just following the logical mathematical steps. And validated derivations can be used in other derivations. You could, if you validated one, you can go throw it into another one, and then you can keep going. And you could also brute force validate derivations with a computer. So you could see if the model is correct by just throwing it in and calculating a whole bunch and seeing if the theory or the equation holds up for many different scenarios. And so these aspects can be categorized as the term, quote, logic, which is severely lacking in the world right now. With this in mind, let's dive right in. So like always, it's a calculus book reference, the one that I mainly use. So note that I mainly follow along the following calculus book. And this is called Calculus Early Transcendental, 6th edition by James Stewart. Alright, so let's dive right in. So topics to cover. So note on applied projects, applied project, radiation from the stars. There's 5 questions. And then we go over the solutions and solution to each one, 1, 2, 3, 4, 5. And then also go over a quick review of Planck's law, and then also an MES note on Planck's constant, which is some pretty interesting stuff on what the actual meaning of this and energy and quantization may actually be. So yeah, so make sure to stick around to the end. Pretty interesting stuff. But it's just going to be a brief one. Actually, I was going to do it very extensively, but realized it's a bit off topic. But anyways, let's just dive right in. So note on applied projects. So recall that applied projects are interesting math projects at the end of some sections of my calculus book. In this particular project, they are at the end of the chapter on infinite sequences and series. Alright, so now here's the applied project, radiation from the stars. So any object emits radiation when heated. A black body is a system that absorbs all the radiation that falls on it. For instance, a matte black or matte black surface, or a large cavity with a hole in its wall, like a blast furnace, is a black body and emits black body radiation. MES note, essentially a black body absorbs all incoming light and emits outgoing light that is not dependent on the type of incoming light. The outgoing light is dependent only on its temperature, and a good approximation is a small hole inside a hollow object. So if you have a hollow object like this, there's a small hole. The light that enters just bounces around everywhere and gets absorbed inside the surrounding. And then what is emitted is just dependent on the temperature of this cavity itself. And here's just another diagram here. So the blue light is coming in, it gets absorbed all into the surrounding, and then the red lines indicates, well, the light that's emitted, and it just depends on the temperature of the surroundings itself. And here is another illustration. So as you heat something up, it starts emitting light, and it's in its typical spectrum, just dependent on temperature. The hotter it is, then it gets white hot over there. So note that blackbody radiation doesn't depend on the shape of the object, just the temperature. So yeah, so this one here it doesn't matter if it's round like that or a box. It's going to emit the same depending on the temperature. And here's here's another blast furnace or oven or whatnot. So there's just a hole in the wall. All the light goes in. It just gets stuck inside, and what's emitted is just dependent on the temperature. Yeah, it's all the light that's coming up, and there it is. It's getting yellowish hot, and you could also look at a table of different colors and their corresponding temperatures. So you can see here this is brownish red, then it gets yellowish, and then it'll get yellow/orange. Gets all the way up to white hot. So you could check with this one here. That's about in this case 1,000 degrees Celsius around there. Yeah, so that's what this hottest part of it is. And there's a spectrum. So there's a spectrum of light there. This one at the reddish over there, it's going to be somewhere about 760, and then you have the hotter parts going at 1200 degrees. All right, let's just keep going further here, and then yes, if you graph if you're to graph what's emitted in terms of its wavelength of the light, and then you can see that the hotter it gets, the wavelength decreases, or the frequency of the light increases as wavelength decreases. And again, just depending on temperature, and this is the amount of light of that wavelength that gets emitted over there. And so note that the temperature of the sun is 5,700 Kelvin, which has a spectral peak mainly in the visible light range. So this is the visible range, and this is 5,000 Kelvin. And so this is a typical one for the sun spectrum. So most of the light that's emitted is in this visible range, corresponding yet to what we can see, and it's where our sun is, which is pretty interesting correlation. So even the radiation from the sun is close to being blackbody radiation. That is, the radiation emitted is almost entirely a result of heat. So all the light that goes into the sun or stars gets absorbed, and what is emitted is just dependent on the temperature. So this scale is similar to this, except instead of wavelength, you're looking at frequency over here. So then the higher frequency is corresponding to lower wavelength over there. And yeah, there's a spectral peak. So as you increase the temperature, you're going to have the shift of the intensity of what's being emitted is shifting over towards the higher frequency wavelengths. So MES note, frequency and wavelength are related to each other. Wavelength equals periodic distance between waves or cycles, and frequency is just waves or cycles per second. For light or radiation, the shorter the wavelength, the higher the frequency and energy. And it's as per the following expression: frequency equals to speed of light c divided by lambda for wavelength. So as you increase frequency right here, that's decreasing wavelength, or you decrease wavelength, frequency increases. So now let's go back to the applied project. So proposed in the 19th century, Rayleigh-jeans law expresses the energy density of blackbody radiation of wavelength lambda as f of lambda equals 8 pi k times t divided by lambda to the power 4, where lambda is measured in meters, it's the wavelength, T is the temperature in kelvins, or K, and little k is Boltzmann's constant. So MES note, Boltzmann's constant is a proportionality factor that relates kinetic energy of particles in a gas with the thermodynamic temperature of the gas. That is, temperature is defined based on the average kinetic energy of a collection of non-interactively moving particles. In other words, they're not attracted or repelling or any other forces that are counted in this model. Boltzmann's constant is also applied to electromagnetic waves. So you could model this particles or waves using this similar model, this Boltzmann's distribution, and with its constant. So anyways, the Kelvin, or K, is the base unit of temperature in the International System of Units, SI. And then also note that water freezes at 273.15 Kelvin, or 0 degrees Celsius, or 32 degrees Fahrenheit. And then it boils at 373.15 Kelvin, or 100 degrees C, or 212 degrees Fahrenheit. So interesting, if you take the difference between these and see the difference between boiling and freezing, we get water boiling minus water freezing equals 100 K, or 100 degrees C, or 180 degrees Fahrenheit, which is pretty interesting then. All right, let's keep going further. So 0K, or absolute zero, is the lowest of motion of ideal gases, which are based on a simplified model of point particles having no spatial dimension and don't have interparticle interactions such as attraction or repulsion. So again, similar to the Boltzmann's distribution of basically infinitely many of infinitely small particles that are just moving around. And yeah, so that's where Kelvin is based on, absolute zero of motion. And then define that as zero temperature. So anyways, going further, so the Rayleigh-jeans law agrees with the experimental measurements for long wavelengths, but disagrees drastically for short wavelengths. The law predicts that the F of the energy density of a particular wavelength goes to infinity as lambda goes to 0 from the right side, 0 plus. But experiments have shown that the actual energy density goes to 0 as lambda goes to 0. So as this lambda goes to 0, this should be going to 0, but instead it goes to infinity. This fact is known as the ultraviolet catastrophe. So in 1900, Max Planck found a better model known as Planck's law for blackbody radiation, and he has this giant equation, which is f of lambda, or the energy density of a particular wavelength. Lambda equals to 8 pi times h, which is Planck's constant, times c, speed of light, times it by lambda to the power of negative 5. And then divided by e to the power of hc divided by lambda kt minus 1. And then where lambda is measured in meters, m, t is the temperature in kelvins, k, h is Planck's constant, which equals to 6.626 times 10 to the power of negative 34 joules times s, or seconds. K is Boltzmann's constant, which equals to 1.3807 times 10 to the power of negative 23 joules per Kelvin. And c is speed of light, which equals to 2.997925 times 10 to the 8 meters per second. So MES note, Planck's constant is the speed of, Planck's constant is considered the, quote, quantum of action, and is multiplied by a photon's frequency to obtain its energy. And we'll get to this at the end of this video. I'll make just a brief note on this interpretation of it. Anyways, going further, so question 1. Question 1 states, use L'Hopital's rule to show that Planck's law results in the following. And then show that Planck's law has this limit as lambda, or wavelength, goes to 0 plus from the right side, or positive side, equals to energy density at lambda, or f of lambda equals 0. So basically, as this wavelength goes to 0, this should go to 0. So in other words, if you go look at this distribution, this lambda of this wavelength, as this goes to 0, this should go downwards 0 for that. So let's keep going further. We'll get to it. And then also show that limit as lambda goes to infinity of f of lambda equals 0. So as the wavelength increases, this should go smaller and smaller as it goes to infinity. So this law models blackbody radiation better than Rayleigh-jeans law for short wavelengths. Going further, so question 2 then also says, use Taylor polynomials to show that for large wavelengths, Planck's law gives approximately the same values as the Rayleigh-jeans law. And then question 3, graph f as given by both laws on the same screen, and comment on the similarities and differences. It says use T equals to 5700 K, the temperature of the sun. And you may want to change from meters to a more convenient unit of micrometers, or where 1 micrometer equals to 10 to the negative 6 meters. No, I believe that's 1 million. So one meter equals 1 million micrometers. If I've I've thought of this correctly. Anyways, going further, so question 4, use your graph in problem 3 to estimate the value of lambda for each f of lambda is a maximum, or for which f of lambda is a maximum under Planck's law. Then question 5, investigate how the graph of f changes as t varies using Planck's law, and in particular graph f for the stars Betelgeuse, t equals 3,400 K, Procyon, t equals 6,400 400 K, and Sirius, t equals to 9,200 K, or Kelvin, as well as the sun. How does the total radiation emitted, the area under the curve, vary with t? Use the graph to comment on why Sirius is known as a blue star and Betelgeuse as the red star. Alright, so now that we've got overall this entire problem, let's just dive right into question 1. Alright, so here's the solutions to question 1. So basically, let's just read that one again. So question 1, use L'Hopital's rule to show that Planck's law results in this. Limit as lambda goes to 0, this one, f of lambda equals 0. So this one here, limit as this goes to 0, show that this equals to 0. The limit as it goes to infinity, show that it goes to 0. And then and it also says use L'Hopital's rule, so it's giving us a hint. And so this law models black-body radiation better than Rayleigh-jeans law for short wavelengths. Alright, so recall, let's go to the solution. So recall L'Hopital's rule from my earlier video, and the earlier video shows that basically, suppose f and g are differentiable, and g prime of x is not equal to 0 on an open interval I that contains a except possibly at a. Suppose that where we have the limit as x approaches a of fx. So if you have this one of fx going to 0, and then you also have limit as g of x is limit of g of x goes to 0 as x approaches a, or you have it going to plus or minus infinity, and the other one is also plus or minus infinity. In other words, we have an indeterminate form of the type 0 over 0 or infinity over infinity. Then L'Hopital's rule says, well, then the limit as x approaches a of f of x divided by g of x equals to, well, the derivatives, the limit of the derivatives. So you can just take the derivative of f prime of x divided by g prime of x. And this is a scenario where g prime of x, this derivative, is not equal to 0 on an open interval that you're looking at, except possibly at a, except at, because again, when you're doing limits, you're not actually plugging in a, so you're approaching that value. So yes, except possibly, but again, it depends on the function, it depends on this scenario. And if the limit on the right side exists, or is infinity or negative infinity. So basically, if this is indeterminate, because you have a 0 over 0 or infinity to infinity, essentially it's saying which side is going to infinity or 0 faster, the top or the bottom. And if it's the top one going to infinity faster, then that means it's going to 0 overall. If the top, if the bottom is going to 0, going to infinity faster, then it's divided by infinity. It's going to go to 0. But if the top one goes to infinity faster, it's going to go to infinity. Yeah, so basically if the bottom is faster, it goes to 0. If the top is faster, it goes to infinity. Anyways, going further. So let's take a look at the following limits while grouping the constants together to simplify the equation. Alright, so let's just write our function down. F of lambda equals 2. Let's see what we have here. Again, this is going to be 8 pi hc and then lambda to the power of negative 5. So let's write this one down. 8 pi hc lambda negative 5. And then we're going to divide this by, then what was the bottom? Bottom is e to the hc divided by lambda kt and then minus 1. So e to the hc divided by lambda kt, then all minus 1. Alright, so now that we have this, and we're going to group the constants together just to simplify it. I'm going to move this lower, move this over here. I'm going to call this part right here, this 8 pi hc, so this part right here, I'm going to call this as a. Yeah, so better you have to put it in this kind of bracket. So this is going to be a. A is 8 pi, let's put a equals to 8 pi hc. And then, so we have that. Well, I'm also going to take this and move it over here. This is going to be, we'll call this b. B equals to, well, just this part here. So hc over lambda k, like that. just so that we have, actually no, we can't put the k there, that's not a constant, I mean the k. I mean the lambda, we can't put the lambda there, we have to put the k. The lambda is a variable, that's this one. So we put this like that. B equals to hc over k, just to simplify, otherwise we're going to be writing a bunch of constants. So this equals to, this is going to be a lambda to the power of -5 divided by e to the b, so this hc divided by this k is going to be, this is going to be b divided by kt. So it's going to be divided by, divided by lambda t. I always get confused, lambda and k and t, like that. I'll just put that bracket around it and move it, and put a -1 over there. So that's what we have. Alright, so now we can take the limit. So limit, let's do the first one. So limit as lambda approaches 0 from the right side, or plus of f of lambda. This equals to limit as lambda approaches 0 from the right side, or the plus. And we're going to put this over there. So a lambda to -5 divided by, divide this by e to the b, and then divided by lambda t -1, like that. Yeah, so now what happens here, as this goes to 0, so this part, this lambda one is going to be, well, a 1 over 0, because this is power of -5, now it goes to infinity. Now this part over here, we're going to have, this scenario is going to be, well, this is going to be, I'll put the whole thing actually. This is going to be e to the, well, this is going to be b divided by 0. So I'll just put it 1 over 0. That's how it's going to look like. -1. This is the same thing as, well, this is 1 to the 0. This is going to infinity. So that's going to go infinity. Yeah, e to the infinity. E to the infinity -1. That's just infinity. So e to the infinity -1 is just going to go to infinity. In other words, we're going to have a scenario of that's indeterminate. So we can apply L'Hopital's rule. Infinity over infinity. Alright, so let's just box this out. So that means we could apply L'Hopital's rule. But before we get to that, let's just do the other one as well. So and, so this one, and let's just do the limit as lambda goes to infinity. Lambda goes to infinity of f of lambda equals to, let's just write this for completeness. We're going to write that exact same thing. That's going to be it's going to be 0 over 0, just by because it's the same equation, but instead of infinity we're going to, instead of 0 we're going to infinity. So power -5, and this is going to be e to the b divided by lambda t -1. Alright, so now when you plug in, this is not 0, this is infinity. When you plug in infinity in this one, you're going to have a 1 over infinity for the lambda, and then this is going to go to 0. And this part right here, you're going to have a e to the, well, 1 over this infinity, that's infinity there, -1. This is going to go to e to the 0 -1, which goes to, well, e to the 0s is 1, so 1 minus 1, which equals 0. So 1 minus 1 goes to, so you're approaching 0. So this goes to a 0 over 0, and also an indeterminate as per L'Hopital's rule. So we have both 0 over 0 and infinity over infinity, like that. Alright, so yes, in both cases we could use L'Hopital's rule. So let's go further. So let's do the limit at infinity first, just because it turns out to be the easier. This one you have to do it multiple times for the L'Hopital's rule. So let's do this one right now first. The limit as lambda goes to infinity of f of lambda equals 2, and so we're going to look at this over here, but instead of writing equals to, I'm going to put the L'Hopital's rule. You could use this notation, equals to with an h on top, so we're going to do L'Hopital's law on it, and this equals to limit as lambda goes to infinity of now the derivative on the top and bottom, d over d lambda of this top part, which is our a lambda -5, like that. Alright, and then we're going to divide this out by the derivative of this denominator there. So derivative d over d lambda of this in bracket, close bracket. So e to the b slash lambda t, put it like that, like this, then minus 1. Alright, so now let's do the derivative. So on the top one, we know that this equals to, well, let's put this down, this equals to, let's put it over here, equals to limit as lambda approaches infinity. So lambda approaches infinity of, well, a, and then we're using our power law, this -5 goes down. So this is going to be negative, so -5 goes down, and we're going to have then we subtract the power, 6. So -1 on the top is going to be -6, like that. And let's just move this in the center. And then this is going to be like that, divided by, now this one, well, this is -1, the derivative of that is just going to go to 0. So we can just leave that out. So now this, all we need to care about is this one here. So e to the b, so this is the exponential function, the derivative is itself, but you have to apply chain rule. The derivative is itself, e to the b divided by kt, like that. And then we multiply this by, again, chain rule. So now we take the derivative of this inside, so b over lambda t. Yeah, now we have to use chain rule, so the derivative of this top part inside, well, that's just going to be, let's just write this over here for completeness, d over lambda of, I'm going to move this like this, b times lambda t to the negative, this is to the -1. So that means we're going to bring down a -1, and then it's going to be negative b over, and then we're going to subtract by power, so that's going to be a 2 there. So then I'm going to put this like this. This is just a bubble to see how we're calculating it out. Yeah, just put it over there, and then this is going to be -1, and when you subtract it, when you do the power law, so you move this -1, then it's going to be -2. So a -2, or just divided by like that, lambda t to the power of 2, like that. And then we have to do chain rule again, which is the inside, so multiplied this. So this part right here is this. Then we have to multiply it by, just for a refresher. Okay, so this is going to be, now chain rule is the inside one, is going to be d over d lambda of this inside function, so lambda t. Like that. And that derivative is just, well, t times by t. And I'll just move this over here. That's just over there. I'll just leave it like that. Put it all inside. So this t like that. That's this one, and then this one is over there. Yeah. Let's do a better bracket. Okay. Alright, so now let's move all the constants out of this limit, using limit law. So we could move this -5a out of there. So we're going to have a -5a, just to simplify it further. Now we could remove all this stuff. So we can remove this -b. Yeah, this -b at the bottom. But also notice what we'll have there. This is, so we have this divided by lambda t squared. But also we have to have this t over there. So just take that another constant, the t over there. Yeah, but so that t goes at the bottom, but this one's divided by t squared and lambda squared. So that means this has to flip on the other side. So then we're going to have a t squared on the top. T squared like that. And then this lambda is going to be on the top squared. And we're going to get to that soon. Just going to be times it by limit as lambda approaches infinity of, now we're going to have this, yeah, so this divided by, so we have this this number divided by this divided by lambda t squared. So then again, those just flip on the top. So we're going to have a lambda squared times it by lambda to -6. And then we're dividing this all out by what's remainder is just this part here. Yeah, that's actually the only thing that's remaining. E to the b lambda t. Alright, so now let's do some cancellations and simplification. So this plus, this negatives become a plus. This t squared cancels with this. So what we're left with now is this equals to, and also this combines with this one here, so this becomes a negative 4. This can be a 5a over b limit as lambda approaches infinity of, now we're going to have a lambda to the negative 4 over e to the b lambda t. Yeah, and also forgot to add a t there, so there's a t over there. Alright, so now we're going to evaluate our limit, and let's plug in the infinity over here. So the top part is going to be a, well, 1 over a infinity goes to 0. And then this bottom one over here, this is approaching, let's see, let's put an arrow. So this is approaching e to the 1 over infinity, which is approaching e to the 0, which is approaching 1. So e to the 0, or any number to the power of 0, is yet defined as 1. So in other words, this equals to 0 over 1, which equals to 0. Like that. So there we've solved the first one, or one of the conditions of the problem was show that this goes to 0 as the wavelength goes to infinity. The next one is to show that as wavelength goes to 0, that the function also goes to 0, as opposed to this one's to infinity. So now let's keep going further. Alright, so now if we look at the limit at 0, so the limit at lambda is approaching 0 from the right or positive side, requires several iterations of the L'Hopital's rule. So if we were to take the limit, so we're going to look at this case here, but again, it's the same function, we're just changing the limit. So we're going to go, so we'll start off where we ended off over here. So we're going to go limit as lambda approaches 0 plus, from the right side, of f of lambda. This equals to, well, we'll put the h in there, and start off where we left off here. So this is going to be 5a t over b times it by a limit. Instead of infinity, we go to limit to 0 plus. And this is going to be of lambda to the negative 4 divided by e to the b lambda t. Alright, so now when you plug in 0, what we get on the top is, well, we have a 1 over 0 that goes to infinity. The bottom is going to be, well, a e to the 1 over 0, which goes to, well, 1 over, this is going to be e to the infinity. So 1 over 0 is going to go into infinity. This goes to infinity. So in other words, this equals to an infinity over an infinity, which is not good news. Alright, so this is still indeterminate, but note that each time we use L'Hopital's rule, we gain a factor of lambda in the numerator, as well as a constant factor, and the denominator is unchanged. And we could see this right here, so we could keep going using the L'Hopital's rule. So let's just write this down. Limit as lambda approaches 0 from the right side of f of lambda. This is going to be equals to with the h, so L'Hopital's equals to, and we're going to start off where we ended up on this one. So put the h on top there. This is going to be 5a capital T over b, and then this is going to be limit. Yeah, limit of this one. Let's just solve the full derivative. So this one, take the derivative of that. This is going to be a limit as lambda goes to 0 plus 0 from the right side. This is going to be lambda to the negative 4. The derivative of that is going to be, well, negative 4 times it by lambda to the negative 5. And then divide by the bottom is going to be, well, using the same exponential rule for derivative, and then chain rule multiple times. We're going to get a e to the b lambda t times it by chain rule. Chain rule means we're going to have at the bottom, it's going to be a negative b. This is yes, this is power of so this is divided by lambda t, or in other words, multiplied by lambda t to the power of negative 1, and then it's going to be a lambda t squared. This square bracket like that. And then times it by, again, chain rule inside, this is going to be t. This will be exactly the same thing over here. So this is going to be negative b, because this denominator is the same thing. So we're going to get the exact same one each time. So negative b divided by lambda t squared, and then times by t. That's exactly what we have here. Then we take out the constants again, or just simplify it. So we can have, there's a negative here. Let's just cancel all the negatives. Negatives cancel. Negatives cancel. We're going to have this 5 times 4 is 20. There's a t there. T cancels. T over there cancels. And this t squared goes on the top. This lambda squared goes on the top. So this equals to, let's write this down as 4 times 5 is 20. Divided by 40 times by, this is going to be a t squared. So this t squared goes over there. As you're dividing by and then dividing by again. So that just flips, goes over there. And then this b is just by itself, like that. And this is going to be times by a limit as lambda goes to 0 plus. And this lambda squared is going to go on top, like that. And then also, I forgot that there's a b there, and there's a b here, so that's going to be b squared, like that. And then we're going to have now, this is going to be lambda squared times it by lambda to the power negative 5 divided by e to the b, like that, kt. Or we could simplify this further, just save time. This is minus the, so negative 5 in the power of 2, that just becomes negative 3. Add those powers together. So this is what we have now. And now this scenario, because we have the exact same thing, so nothing changes in this one. All we have is the constants and change. So this is the exact same as this, except this instead of negative 4, it's a negative 3. And that's going to be, it's going to be the same thing. 1 divided by 0, it goes to infinity. And the bottom is 1 divided by infinity. I mean, this bottom just goes to infinity. So we have infinity over infinity, but this one is 1 less than this. And it's exactly the same thing. So this equals to, let's put this arrow, infinity over infinity. So it's the exact same thing. Yeah, so it's the exact same thing, except we have a constant and this power goes down. So now we can see a pattern. So if we use the L'Hopital's rule 3 more times, the exponent of lambda in the numerator will become 0. So the next time will be negative 2, then negative 1, then it goes to 0. And when it's a 0, well, that's just 1. So then we don't have this infinity on the top. So what we could do is, that is, for some constant ki, just a sequence of these, all constant integer I there, then, and we're going to write this as, this first one's going to be our k1. It's not both ones constant. This is just for this case. So we're going to have, this is going to be k1, like that. That's, and then so then what we're going to have is, well, let's just write this all down, and we can notice the pattern. Limit as lambda goes to 0 plus, or from the right side, of f of lambda, this equals to, or this L'Hopital's equals to, and let's write off where we ended up here. So this is going to be k1 times it by limit as lambda approaches 0 from the right side, and this is going to be negative, lambda to the power of negative 3 divided by e to the b kt. Then if we apply L'Hopital's rule again, just following the pattern, this equals to h equals k2. So we're going to have another constant times by limit as lambda goes to 0 plus, from the right side, this can be negative, lambda to the power of negative 2. And then the denominator is going to be the exact same thing. Lambda t, like that. Alright, so now I keep going further. So then, yeah, keep following the pattern. We're going to eventually get this one here, lambda, this is equals, h equals, or doing the L'Hopital's rule again, because we're going to keep getting a infinity over infinity until we get further. It's going to be k3, and k3 is going to be limit as lambda approaches 0 plus, this can be lambda to the power of negative 1, so we just need one more. Lambda t, like that. So the next one's going to be equals to h. Use a L'Hopital's rule again. We're going to get another constant, the last one, k4, and k4 gets to limit as lambda approaches 0 plus from the right side. This is going to be lambda 0, like that. Then this is e to the b kt. and lambda to 0 is just equals to 1. And this is going to be, well, this one we already know is infinity. So this is just, we already know this is going to be, move this over. Let's move this over like this. Is going to be e to the 1 over 0, which goes to e to the infinity, which goes to infinity. So in other words, we're going to have a equals to a, we're going to have a scenario of 1 over infinity, which approaches, well, 0. It's equals 0. And yeah, that's 0. That's exactly what the question 1 says. So yeah, so this confirms question 1. So now let's look at question 2. Let's just scroll all the way back up to question 2. So again, there is the limits. So we show that the limits of this function of Planck's law approaches 0 for when lambda goes to 0 or lambda goes to infinity. So yes, now let's look at question 2. So question 2 says, use Taylor polynomials to show that for large wavelengths, Planck's law gives approximately the same values as the Rayleigh-jeans law. So we have this law, that's Planck's law, and we have Rayleigh-jeans law over here. And we're going to see that, or show that this is approximately equal to this at large wavelengths. So it keeps going, scroll down here. So we're asked to use Taylor polynomials, so we can approximate Planck's law by expanding the exponential function using a Taylor polynomial. So yes, that's the complicated part of the function is that e to the, see what it was. We have e to the hc divided by lambda kt. So we could replace this complicated function with a Taylor polynomial, which is just basic algebra, but infinite series form. Scrolling back here. So first, a quick recap on Taylor series from my earlier video. So here's the hive notes of it. So theorem of power series, representation or expansion at A, that is if we just have a series like this, if f of x equals to constant times by x minus a, and then it's a power, and the r is the radius of convergence, so x minus r, and yeah, this infinite series converges for this radius of convergence. So for example, if this is the a, then the radius would be up to r here, plus and minus, and the endpoints you have to decide on your own, but this is just between it, it converges. Then its coefficients are given by this formula, Cn equals to nth derivative at a divided by n factorial. And then that's that is how we get a Taylor series. So that's a Taylor series over there, and then you can expand it out. It looks like this. So we plug these inside, so this is going to be f of a plus the first derivative of a divided by 1 factorial times x minus a to the power of 1. And the second derivative, and there's just 2's and there's 3's. And so on. And then here's a table here, which I went over in my earlier video of, in my earlier video and videos going over the Taylor expansion. So for e to the x, you can expand it out, because remember, you're just using the derivatives, and plug that inside, you're going to get this formula. So 1 plus, this is going to be x to the power of n divided by n factorial, or 1 plus x squared divided by 2 factorial plus x3 to power divided by 3 factorial. And this is the radius of convergence is r is equals to infinity. So in other words, it converges for all values of converges for all values of x. So yeah, so that's very interesting stuff. So from the table above, we could use the following Taylor series, which is this e to the x over there. So let's just write this one down. So we could write e to the x and just write it over here. That's the summation, and from like that, yes, so summation from I, or where's this go, n, from n equals 0 up to, this is x to the n divided by n factorial. Now this equals 2, then we plug in 0 inside, this is going to be, x to the 0 is just 1 by definition, and then 0 factorial is 1 by definition as well. So this is going to be 1, the next one is going to be, when you plug in a 1 in there, so x divided by 1 factorial. Then plus x2 divided by 2 factorial. Then plus x3 divided by 3 factorial. Dot, dot, dot. And the radius of convergence is r equals infinity, so for all values of x, it converges. Alright, so thus we have, let's just put in Planck's law. So Planck's law, f of lambda is equal to, just remember what we had, 8 pi hc, then lambda to the power negative 5. And then the bottom is going to be, well, e to the hc divided by lambda k capital T, like that. And then we're going to subtract this by 1. And now what we'll do is we're going to approximate the exponential function with this Taylor series. And what we'll do there is, well, then we're going to call this entire thing over here, that's going to be our x. So that's our x. So this means now, well, this equals to e to the, or actually that's the bottom. So we're getting rid of that. We're going to write this as, let's see how long this is going to be. Let's just make a giant one like that. This is going to be 8 pi hc negative 5. And then plug this this e to the x inside. So that's going to be, we'll put a big giant bracket. Put a bracket like that. It's going to be 1 plus, now x, the x divided by 1 factorial is just x. That's going to be just, well, x over, this is going to be hc lambda kt. And yeah, remember, this is just our x. X like that. And now the next one's going to be plus, this is going to be x squared, so, and then divided by 2 factorial. So let's put the 2 factorial outside. So 1 over 2 factorial, and then we're going to have a bracket, and this is going to be our x. This is our hc over lambda kt, and then squared. And then the next one's going to be plus 1 over 3 factorial, and this is going to be hc over lambda kt, and this is going to be, let's write this neater, cubed. Alright, so then yeah, we have that, and then it basically goes on to infinity, so we go plus dot dot dot, and then put a bracket, and then minus 1, part of the equation over here. So if we replace it with that giant Taylor series, let's just move it like this. And yeah, so now since we're approximately trying to show, so we're trying to show that we're basically trying to approximate it with the Taylor series. Instead of going infinity, so let's go back to what it says. For large wavelengths, show that approximately is the same as the Rayleigh-jeans law. So what we'll do is, well, we'll notice that outside of the first term, so there's no squared here, but now you're squaring the wavelength. So let's say this wavelength is large, then if you're going to square, that's just double as large. Then you cube it. Now you're going pretty much much larger, and you also have these factorials over there. So then these are going to be, the bottom's going to be very very large, and then so what that means is, yeah, so for large wavelengths, and you also have these factorials, this over here is going to be approximately small. So this is small as lambda is large. So as it goes to infinity, it's just getting larger. Yeah, this is getting larger. I mean, this whole thing goes to smaller and smaller as this lambda gets larger and larger. Yeah, because remember, hc are constant, so they're not changing. But so if you increase k, so as you get more and more, as you get larger, and I mean increase lambda as you get larger and larger, all you're doing is making these later terms smaller and smaller. Yeah, so if we approximate that by only looking at the first term, so what that means is, well, this will equal to, so we're going to only take this first term, so this first non-zero term there, or non-trivial term. So we're just going to cut off from here. Approximate. Let's go approximate from here. Approximate. So we're going to approximate here. So this is going to equal to this. The center of this equals to now, or roughly equals to 8 pi hc lambda to the power of negative 5 over, and we're going to have a 1 plus hc lambda kt. And we also have this negative 1 there. Then this cancels. This cancels. This equals to 8 pi hc lambda, or actually before we even do that, we have the we have to cancel out some stuff. So we cancel out these negative ones. I'm just gonna put this actually like this. Put the bracket just to show that it's this bracket there. And then now once we cancel those out, now we can divide this out. So this h cancels with this, c cancels with this, and then what else do we have? This cancels. Yeah, this lambda cancels with one of these, so it becomes a 4. So what that means is this becomes 8 pi, and where, yeah, this one here, so 8 pi, this is divided by k there. So this is a this numerator divided by denominator where the denominator has the denominator of k, so that k gets flipped upside down, as well as this t, so we just flip it all the way up. It's going to be kt. And this is lambda to the power 4, that just goes downwards. So that's just lambda positive 4 at the bottom. And this is just Rayleigh-jeans law. And we can check mark this. And you could actually scroll up there. So 8 pi kt divided by lambda 4, and scroll up to the Rayleigh-jeans law. So 8 pi kt divided by lambda 4. So that's exactly Rayleigh-jeans law. Just fascinating stuff. Let's keep going further now. So going further, this is exactly Rayleigh-jeans law. So thus, since lambda is large and the terms of the Taylor series are very small compared to the first non-zero term, approximating Planck's law using just the first Taylor polynomial T1, or the first non-zero or trivial term, yields Rayleigh-jeans law. So I just typed up what I just said and did. So anyways, yes, that is the solution to question 2. Alright, so now let's take a look at question 3, and let's just scroll all the way up to question 3 and read it again. So question 3 states, graph f as given by both laws on the same screen and comment on the similarities and differences. And then it says use T equals to 5,700 Kelvin, which is the temperature of the sun. You may want to change from meters to the more convenient unit of micrometers, where 1 micrometer is equal to 10 to the negative 6 meters. So in other words, this micrometer, I think that's mu symbol, another Greek symbol, and then 10 to the negative 6, so that's 6 decimal places. In other words, this is, or 6 zeros, or in other words, this is 1 meter equals to 1 million micrometers. And since we're dealing with very small wavelengths, you want to just scale this up, or just use a smaller unit over there. So let's just scroll down there, keep that in mind, and let's go all the way here. So solution to question 3. So to convert to micrometers, we multiply lambda, which is a wavelength in meters of the equation, times it by 10 to the 6, and this is just 10 to the 6 micrometers divided by meters. Or you could also divide it by 10 to the negative 6 if you want. If you want to use that conversion that we were given. But anyway, so we multiply lambda of meters times by 10 to the 6, which is of micrometers, divided by meters. This is the conversion, and then we get equals to lambda in micrometers. So this, you could just use our basic units, and those just cancel, and then we're just left with this one here. So anyways, so going further, so this is an Excel sheet that I made. Here's a link to it. You can download, and you can click and download and view it there. But I'm just going to show the charts that I made. So here's the energy density, F of lambda, and the units are. And the units here, I kept these as metered there, just because the calculus book chart is the same thing. But the wavelength, I just keep it at micrometers. So energy density in terms of joules, energy divided by meters cubed, and divided by m. So they separate this just so it looks like it's energy density of volume per each wavelength. So there's the m over there. And then here's a wavelength right here, so in micrometers. So we convert it so that's small numbers, right? Like this, instead of going 15 times 10 to the power negative 6. Just multiply that out. So here is the two graphs. So here's from 0 to 30, but I've also made this from 0 to 500 on the energy density right here. So that, so it's not that high, but you can see the similarities here for the blackbody radiation. So Planck's law is the solid black line, and then Rayleigh-jeans law is the dashed line. You can see it's pretty well matches up at higher wavelengths. This gets higher here, and then this is pretty much similar to it. But then if you go, if you look at shorter wavelengths, and then also change up the scale, so you could see it better at shorter wavelengths. So here's what happens at shorter wavelengths here. So Planck's law again. Notice Planck's law goes like this and goes down. Then Rayleigh-jeans law just keeps going, skyrocketing up there to infinity. So yes, the first figure shows that the two laws are similar for large lambda. So large wavelengths, these are all similar. So it's matching up over here. Then once you get below this, it starts messing up. So this one here, so this is above 10, even above 5. Then once you get below wavelength of 4 or 3, all the way closer and closer, smaller and smaller, there's a big divergence here. It just gets bigger and bigger and bigger until it goes to infinity. So the second figure shows that the two laws are very different for short wavelengths. So here's short wavelengths. This is again the ultraviolet catastrophe. So the UV catastrophe, because the original theory, the Rayleigh-jeans law, was showing it's skyrocketing up, which should mean that hot objects should be showing really high intensity of short wavelengths like UV and so on. But in actuality, it dips down. So once you get past this visible range and for the sun, then it just dips down. So you don't get a lot of these high frequency waves. All right, keep going further. So Planck's law gives a maximum at, in this case, lambda is equal to 0.5 micrometers. So right about over there is the maximum. And so there's the peak of the peak energy density or intensity. So most of that light that's coming from the sun is in this 0.5 micrometer range. And then while the Rayleigh-jeans law gives no maximum or minimum, it just keeps going. Yeah, so there's no maximum there, it just keeps going infinity, and there's no minimum either, whereas this one here, the minimum goes to 0 over there for the Planck's law. So yeah, that is question 3. So now let's look at question 4, and what was question 4? Scroll up. So question 4 says, use your graph in problem 3 to estimate the value of lambda for which f of lambda is a maximum under Planck's law. So we already did that one. That's just 0.5 micrometers. So from the graph in question 3, f of lambda has a maximum under Planck's law at lambda is approximately equal to 0.5 micrometers. So there's the maximum over here. This is the max for Planck's law, and that's straight over at this 0.5 micrometers. All right, now let's do question 5. Question 5 is going to be comparing different stars. Okay, where's question 5? All the way here. So question 5 states, investigate how the graph of f changes as t varies using Planck's law. In particular, graph f for the stars Betelgeuse, t equals to 3,400 Kelvin, Procyon, t equals 6,400 Kelvin, and Sirius, t equals 9,200 Kelvin, as well as the sun. And then how does the total radiation emitted, the area under the graph, vary with t? And then says, use the graph to comment on why Sirius is known as the blue star and Betelgeuse as the red star. So let's scroll all the way down to question 5, the solutions. So solution to question 5. So using Planck's law, we investigate how the graph of f changes for different temperatures of stars. So here's Betelgeuse 3,400 Kelvin, and then there's Sun 5,700 Kelvin, and then it just is increasing right here. Then Procyon 6,400 Kelvin, and Sirius 9,200 Kelvin. So here's a graph that I made from that same Excel sheet, so you can see it's all there, the table and so on if you want to play with it. So here's blackbody radiation, Planck's law, and yes, so this is all Planck's law. The black one here is the sun, so this is the sun. And then you have Procyon is over here. Yeah, so that's the sun there, and this red one is Betelgeuse over there. So that's B. And then we have Procyon is this dashed line here, and also this one's Sirius. So I gotta update this. Just gonna delete this, and I'm just gonna update quickly the copy and paste. Just updated right now. Just updated this. So there it is. I just updated. So there's a Sirius one there. So this is the Sirius. This is sun is the black one, and then you have Procyon. And then we have the red star Betelgeuse, and I made this blue for the blue star there, and this is the red star Betelgeuse over there. So B at this red one. So you can see the difference right here. So this is the Sirius is the super hot sun, 9,200 Kelvin. Notice that it spikes up, and they're all shifting their peaks over. So this peak is over here, this peak's over here, this peak's over here, and this peak is somewhere down there. We're gonna zoom in on that soon. So it's all shifting the peaks to the left to the higher frequency range. And then here's a zoomed in look at Betelgeuse over here. So here's zoomed in. So I just take this section over there and zoom in. I'm just gonna remove this because it's pretty obvious which one is which. All right, so there's so it looks like that. So yeah, notice this one. This is the colder star, so 3,400 Kelvin, and then there's the hotter one over there, the sun. And yeah. So it keeps going further. So as t gets larger, the total area under the curve increases. Yeah, so the total radiation emitted as it gets larger. So this area is going to be much bigger than this one. So hotter sun emits more radiation. So the total amount is more, and intensity is shifted over to the left. So this one is much more. You can see it engulfs the entire thing. And then this one also engulfs all of the one below. So yes, the more energy it emits. Let's go read it again. So as t gets larger, the total area under the curve increases, as we would expect. In other words, the hotter the sun, the more energy it emits. Also, as t increases, the lambda value of the maximum decreases, i.e. shifts to the left, or shifted to the left. So the higher the temperature, the shorter the peak wavelength, and consequently the average wavelength of light emitted. So yes, the total one right here, if you want to see the average wavelength, it's going to be all shifted to the left as you get higher temperature. Everything's shifted to the left over here. So yes, so keep going further. So this is why Sirius is a blue star and Betelgeuse is a red star. Most of Sirius's light is of a fairly short wavelength, that is a higher frequency toward the blue end of the spectrum, whereas Betelgeuse's light is of a lower frequency toward the red end of the spectrum. And so here is a approximate wavelength in meters, and this is in micrometers of, this is the visible range. So this is the gamma rays, so super small wavelength, but high frequency, and radio, super large wavelength, but very low frequency. And then this is the visible range right here, as at the 0.39 to the 0.7. And then if you look at it here, let's just look at, so here's Betelgeuse, and this is at, it's peaked at around over here. So if you look at where the big chunks are, so around 0.8. So around 0.8, so in other words, yes, 0.8, 0.7, 0.8. Around this point, this is the red side, or Betelgeuse. Let's say B. Yeah, so that's Betelgeuse over there. Let's erase this for neatness. And then if you look at the other one here, the big, the blue star, the Sirius blue star, you can see that's peaking around between over here and here. So about 0.3, and then above 0.4, so about 0.3 to 0.5. And you can see here 0.3 to 0.5 around there. This is the blue star. So this is a Sirius. This. Alright, so that is all the questions in the plot project. And now, just for more context, I'm going to go over Planck's law and then later make some notes on Planck's constant, which is pretty interesting stuff. So a quick review of Planck's law. So for more context, let's go over a quick review of Planck's laws from the Wikipedia. Just gives a mainstream narrative of everything. And so here's mainstream narrative of Planck's law. So Planck's law describes the spectral density, is essentially what we were doing, basically the density of the different types of wavelengths emitted, of electromagnetic radiation emitted by a black body in thermal equilibrium at a given temperature T, when there's no net flow of matter or energy between the body and its environment. So yeah, basically there's when you have the radiation inside, then it's going to emit heat-based radiation outwards, and so on. At the end of the 19th century, physicists were unable to explain why the observed spectrum of blackbody radiation, which by then had been accurately measured, diverged significantly at higher frequency from that predicted by existing theories. In 1900, Max Planck heuristically, or in other words by trial and error method, derived a formula for the observed spectrum by assuming that a hypothetical electrically charged oscillator in a cavity that contained blackbody radiation could only change its energy in a minimal increment E that was proportional to the frequency of its associated electromagnetic wave. Yeah, so this oscillator, or heat, or vibration of charges or whatnot is they're pretty much intricately linked. Yeah, so it's basically when Planck's law considered the energy emitted is only in increments, then this resolved the problem of the ultraviolet catastrophe predicted by classical physics, or that Rayleigh-jeans law. This discovery was a pioneering insight in modern physics and is of fundamental importance to quantum theory. So the law, every physical body spontaneously and continuously emits electromagnetic radiation, and this spectral radiance, or in other words wavelength divided by frequency, wavelength or frequency, not divided by, wavelength or frequency spectrum of emitted radiation, which is again similar to ours. Ours is just an energy density per volume of a body. B describes a spectral emissive power per unit area per unit solid angle, or the angle of projection for particular radiation frequencies. The relationship given by Planck's radiation law given below shows that with increasing temperature, the total radiated energy of a body decreases and the peak increases. Yeah, so the total radiated energy of a body increases and the peak of the emitted spectrum shifts to the shorter wavelengths. As I just showed, everything gets shifted to the left. According to this, the spectral radiance of a body for frequency V at velocity, at absolute temperature T is given by this equation. The spectral radiance B of function of frequency and temperature equals to 2h, which is Planck's constant, times frequency cubed, times it by 1 over e to the power of hv divided by k, Boltzmann's constant, times temperature minus 1. And this is divided by c squared. So it's slightly different than ours, but this is spectral radiance, and we'll show you how show you the equation that we use in the applied project shortly. So where kb is Boltzmann's constant, h is a Planck constant, and c is the speed of light in the medium, whether material or vacuum. So again, here's that graph we had. So there's a visible light over there, and remember this is 5,000 Kelvin. The sun is 5,700 Kelvin, so it's similar there, but yes, it's in the near the visible range and some UV as well. And this is the classical Rayleigh-jeans law, and it just keeps going up and up. And notice how all the peaks shift over to the left. The peaks go to the left, and it goes up much higher, so higher energy emitted. So Planck's law accurately describes blackbody radiation. Shown here are a family of curves for different temperatures. The classical black curve, it diverges from observed intensity at high frequencies or short wavelengths, so over here. All right, going further, so note that the solid angle, so this part right here, this is over here per unit solid angle. Just to illustrate what they mean by that, is note that the solid angle has units of steradians and is the angle of the projection of a specific area on the surface of a sphere. So if you have radiation from this zone there, if you have this W there for solid angle, then there's going to be a projected area on this surface over there. And again, it's just an equation forward, and this is just to illustrate what they mean. Right, so this is used to quantify the amount of radiation projected from a heat source. There's another image of it, so that if that's the sun radiating, then this is the solid angle. This is the area of the quantified solid angle that they are deriving. Yeah, which could be somewhere over there, like that. Anyways, I don't want to get into that detail too much, but that's just an illustration of an idea of how they quantify the radiation emitted from a black body or the sun, and so on. So note that the equation used by the above Wikipedia article is not the exact same one as the one my calculus book used, but we see the version used from the following Rayleigh-jeans article. So yeah, again, this one doesn't have the 8 pi in there, and we'll get to that in a bit. So going through the Rayleigh-jeans law from the Wikipedia. This one states, in physics, the Rayleigh-jeans law is an approximation to the spectral radiance of electromagnetic radiation as a function of wavelength from a black body at a given temperature through classical arguments. For wavelength lambda, it is, we'll have it over here, the spectral radiance of this is B of lambda of the wavelength at given temperature equals to 2 times T divided by lambda 4, where B lambda is a spectral radiance, the power emitted per unit emitting area. Per unit emitting area per steradian, that's solid angle unit, per unit wavelength, and C is the speed of light, KB is a Boltzmann's constant, and T is the temperature in Kelvin. For frequency V, I don't know why they use V instead of F, the expression is instead BV, this is in wavelength, this is in frequency, so BV of T equals to 2 frequency squared k sub b is subscript b of T divided by c squared. The Rayleigh-jeans law agrees with experimental results at large wavelengths or low frequencies, but strongly disagrees at short wavelengths, high frequencies, as I showed several times. This inconsistency between observations and the predictions of classical physics is commonly known as the ultraviolet catastrophe. Its resolution in 1900 with the derivation by Max Planck of Planck's law, which gives the correct radiation at all frequencies, was a foundational aspect of the development of quantum mechanics in the early 20th century. And then going further into that article, says it says in other cases, Planck's law is written as, you can write this as U of V of frequency times temperature equals to 4 pi over C times times it by the spectral radiance BV of T for energy per unit volume. In other words, the energy density. So that's what we were graphing or solving in our applied project. In this form, the Planck function and associated Rayleigh-jeans limits are given by, so you could write this energy density as this, u of wavelength times u of wavelength and temperature equals 2, or a function of wavelength and temperature, lambda equals to 8 pi hc divided by lambda to the power of 5 times by 1 divided by e to the power of hc divided by lambda kb times t minus 1. So this is our Planck's law. And then the associated Rayleigh-jeans limits, when you take the limit or approximation as we did, you get to this 8 pi kb t divided by lambda 4, which is exactly our function that we were given in the applied project. So yes, I mean, note these are the equations used by my calculus book in this applied project. So we looked at energy density. And you could also write this in terms of frequency instead of wavelength, and this is the equation. So U of frequency and temperature equals to 8 pi h times frequency cubed divided by c cubed, and then times it by 1 over e to the hv divided by kbt minus 1. And this is approximately equals 2 when you simplify it to make it reduce into Rayleigh-jeans law, and you get to this 8 pi kbt times frequency squared divided by c cubed. Alright, so now that we have that, now the reason I went over to that, this note or this context on it, because I want to make a note on Planck's constant, and there's pretty interesting stuff. So anyways, let's just keep going further. So MES note on Planck's constant. Alright, so MES note on Planck's constant. Planck's law was able to better predict blackbody radiation by modeling energy as discrete packets called quanta, which ushered the start of quantum, which ushered in the start of quantum mechanics. I had initially written up additional information on Planck's law and its derivation, and it was pretty extensive, but I have since removed it as it was too far off topic from the straightforward applied project. My initial reasoning was to compare the mainstream interpretation of Planck's constant of being a, quote, quantum of action with Laurie Gardy's, a YouTuber over here, interpretation that it is in fact the quantum of, quote, energy. And the following links I recommend as reference for further research. So this is derivation of Planck's law by Physics Explained. It's a decent derivation of it. And I was, in fact, when I was writing up, I went pretty much step by step of the derivation that they had and included it in here. Then realized maybe just save that for another video. So then another reference that I recommend is, so Cycles and Planck's Constant by Laurie Gardy, aka Fractal Woman. And this is an Hive article that I wrote, and I put a bunch of links to her videos and paper over there. And also another article that I wrote referencing her paper and her notes is a modified unit analysis, and this is on the types of units, or the unit analysis that she does, and it basically includes the cycle. So whenever you have frequency or wavelength, she always includes the cycle, and then you get some very interesting interpretation that arises from this viewpoint. So anyways, so the derivation of Planck's law, just for a quick summary, the derivation of Planck's law involves quantizing energy as an integer number and multiplied by Planck's constant h and multiplied by frequency f. And this is from the derivation video right here. So here's just a screen grab from this. So the birth of quantum mechanics. So energy is quantized according to Planck equals to n times a minimum increment, which is this epsilon. And then he determined that is equal to Planck's constant times frequency. It's related, so it's proportional to frequency. So n h f. And then this is the classical one, is just energy is you have infinitely continuous, so there's no discreteness. So you have energy at every decimal place. Just keep scrolling all the way up. And then the quantum one, you have energies either 0. This is the next one is going to be hf. Then the next one's 2hf, and the next one's 3hf, 4hf. So it depends on the frequency. The use of the frequency term in the quantized energy equation is interpreted as the usual quote wave particle duality photons with different discrete energies. So, for example, if you have E equals HF, so that's that is the minimum energy for each frequency. So then you're going to have different types of quote photons or photon particles. And so you're going to have one with an energy a wavelength that's different than this one. Another one's different than this one. But then you're going to have each the amount of energy is going to be that h constant times the frequency. So you're going to have a bunch of different shapes over here. So this one's long, this one's short. This one's a long wavelength, but you're going to have a quanta of that. Then you multiply the integer value to get total of them. And then here's also the wave particle duality picture. So you have a wave, you have a particle, and there's the wave in there, and then you basically quantize it. But there's an interesting aspect that I didn't realize until I came across Lori Gardy, aka Fractal Woman's YouTube channel, which has some pretty interesting insights. So the physics investigator, it's a good term, Lori Gardy argues that since the frequency term has units of cycles per second, then the conventional quantized energy equation is actually for a single second or unit of time. Because remember, it's cycles per that second. So if the frequency has frequency 10 per second, then there's that unit of time that's in there. This means that instead of quantizing quantized energies for each frequency, because if you're using a different unit of time, for example, instead of seconds you use hours, you're going to have a different frequency term. So then, in other words, frequency is not a fundamental, or you can view it as not a fundamental thing. So instead of quantizing, let's say if you have a high frequency, you're going to quantize this one, it's going to be a different shape than this little tiny one. So going further, I'll read this again. So this means that instead of quantized energy for each frequency, instead light may be viewed as being made up of a single quantized energy, and this would be Planck's constant, which corresponds to higher total energy for each second or unit of time. Or actually, instead of writing the last, it's a higher total energy for each or actually better, I just rewrote that sentence. So let's read this again. So this means that instead of quantized energies for each frequency, instead light may be viewed as, light may be viewed as being made up of a single quantized energy, Planck's constant. Thus, the more quantized energy units per unit time corresponds to a higher total energy. So yes, if you have, this is from our paper, so figure 1, 3 different wavelengths or / frequencies of light. So here's a unit of time. So if you have a lot of these quantized energies in there, this is going to be higher energy and higher frequency. And then in this unit of time, this can be lower frequency, but you're going to be at lower energy. This is super low frequency, but again, each one of these is exact same energy as this. These ones are all the exact same. So a high energy quote photon. So instead of circling all these as a photon, so this would be mainstream physics would be like this is a high, this is a high wavelength, low frequency photon, and this is another photon. And this is another photon. This is a different wavelength and different frequency. So instead of that, Lori says no, it's actually, they're all made of the individual discrete energy units. And then when you have this unit of time there, that's where you get the frequency, and basically the more of these that are compact in space and time, then that's more energy, less energy. So in this interpretation, the frequency is an emergent or more abstract concept made up of many quanta of energy. Yes, it's made up of many of these. I'll be exploring this further, so stay tuned. It's pretty fascinating stuff. This might be key to a lot of things. Anyways, that is all for today. Hopefully you enjoyed and follow along. And like always, all the you can download these exact notes in the link in the description below, as well as Excel sheet and so on. And also, you could view all these notes on the Hive blockchain in article format. So, anyways, let's scroll all the way back up. Anyways, that's all for today. Hopefully, you learned, and stay tuned for another math easy solution.